Hello class. So in this video, we're going to start taking a look at comparing proportions between two different populations. So we've done a lot of work so far this year with confidence intervals, which is where we want to estimate one single parameter about a population, and significance tests when we want to test for or test against a particular hypothetical value for a parameter for one population. But there's a lot of scenarios out there where we would want to compare two different populations and see if there's a difference between the two. So we're going to take a look at some examples of comparing two different populations, and we're going to look at a particular confidence interval that allows us to estimate how different a proportion is between two different populations. So let me see if I can pull up the examples that we have, or we're going to take a look at here. So let's see, where did those go? There we go. So this is going to take us into section 10.1, which is about comparing two different population proportions. So here's some examples of a question we might solve, or a question you might answer using the things we're going to learn in this section. You know, how different are the proportions of hockey fans in the US and Canada? Are the proportions of conservatives among young and old adults significantly different? Is there a difference in the proportion of AP Stat students and AP Calc students who plan to take the AP exam? You know, or do Stat students take the exam more often? Calc students take the exam more often? Do they take it about the same? That's a question we can answer with the skills in this section. All of these questions, what they have in common is that they refer to a difference in proportions between two separate independent populations. It's all about a categorical variable we're measuring, and do the proportions that fit in that category, do that proportion differ for two different populations? So what we're going to look at in this video is how to estimate how different those proportions are using an interval we call a two-proportion Z interval. A two-proportion Z interval compares the proportions for two different populations and estimates how different those proportions are. These are the condition checks that we would need to be met for each of the two different samples. So we would need both samples to be random. So we have a random sample from one population and a random sample from another population. We also need n times p and n times 1 minus p to both be at least 10 for each individual sample. So we need at least 10 successes and fails from the first sample and at least 10 successes and fails from the second sample. And we also need, in the third condition, both of those samples to be independent. And that means that, for one thing, they don't influence each other. And another thing is, if we're sampling without replacement, we need the population size to be at least 10 times the sample for each different sample. So we're going to be checking these conditions for each individual sample. The formula that we're going to look at for the standard error, we're going to use that when we're dealing with confidence intervals as well as significance tests. For proportions, really it's the combination of two individual standard errors combined together. So we've seen in the past that for one population, the standard error is p times 1 minus p over n, the square root of that. Now, when we combine those together, what we essentially do is we square them both, add them together, and then take the square root. And so what we end up with for the standard error when we combine two populations is this big square root, p hat 1 times 1 minus p hat 1 over n1, that's for the first sample, plus p hat 2, 1 minus p hat 2 over n2, that's for the second sample, and it's the sum of those two. When we put that together as a confidence interval, our estimated difference is p hat 1 minus p hat 2, plus or minus z star is our critical value, and that's the number of standard deviations or standard errors we go to get a certain percentage, so that we can get off of the table, times that standard error, square root of this sum, p hat 1 times 1 minus p hat 1 over n1, plus p hat 2 times 1 minus p hat 2 over n2. So here's an example of where we might calculate a confidence interval. So let's say we want to compare AP Stat students to AP Calc students, and do they take the AP exam at different rates? Is one group more likely to take the exam than another group? So before we get to an example of the whole process, let's just calculate a standard error. So let's say that in one random sample of 120 AP Stat students, let's say 90 of them said they plan to take their AP Stats exam. And in a different random sample of 100 AP Calc students, 65 of them said they plan to take their AP Calc exam. So I want to calculate the standard error for the difference in the proportion for these two groups of students, stats and calc. So our standard error is the square root p hat 1 times 1 minus p hat 1 over n1. There's our first samples of stat students, plus p hat 2 times 1 minus p hat 2 over n2. There is our sample from the calc students. So what we're going to do is we're going to find the important information. P hat 1 is 90 over 120. In the statistics sample, 90 said they plan to take the exam out of 120 in the group, so p hat 1 is 0.75. Our sample size was n1, which is 120. In the second sample for AP Calc students, we had 65 say they plan to take the exam out of the 100 that were sampled, so p hat 2 is 0.65 or 65%. N2, our sample size of stat student or calc students, is 100. It is okay that these sample sizes don't match each other. We can run the confidence interval either way if the samples match or not. So when we substitute in the parts that we know, p hat 1 is 0.75, 1 minus p hat 1 then is 0.25 over that sample size 120. Plus, for calc students, p hat 2 is 0.65, 1 minus p hat 2 is 0.35 over the 100 calc students. And so calculating that whole standard error gives us 0.0619. What that means is that in many samples similar to these ones that we took, the observed differences of proportions taken the AP exam would vary from the true difference by about 0.0619. So if we took a bunch of different samples like these, the difference between the groups that we would see would vary by around 6% or so. Now let's take a look at taking this example and going through the whole process of calculating a confidence interval. So same example, in a random sample of 120 AP Stat students, 90 said they plan to take the AP exam. And in a different random sample of 100 AP Calc students, 65 said they plan to take the exam. And we're going to calculate and interpret a 90% confidence interval for the difference in the proportion of stats and calc students who plan to take their AP exam. In step 1, we would state what we're going to do. So write out your parameter in context. Our parameter here is not necessarily two different proportions, but it's the difference between the proportions. So we're really estimating P stats minus P calc. What that means is we're estimating the proportion of stats minus the proportion of calc students who plan to take the exam. It's the difference between the two. For example, if we got a difference of 10%, that would mean that there's 10% difference between these groups, that more stat students plan to take the exam than calc students. If we had a negative proportion, or a negative difference, that would mean that less stat students plan to take the exam than calc students. So step 1 again is to state we're going to estimate P stats minus P calc, the difference in the proportion of stats and calc students who plan to take their AP exam. In step 2, we would need to plan what we're going to do and check our conditions. So we will construct a 2-prop Z interval. That's the name of the interval that compares proportions from two groups. And we're going to do that with a 90% confidence level, assuming conditions are met. So condition 1 is our random sample, and both samples were stated to be random in the problem. So the random condition is met. The second one is that we need n times p and n times 1 minus p the number of successes and fails in each group to be at least 10, there were 90 successes in the stats group, which leaves 30 fails in the stats group, 65 successes in the calc group, leaving 35 fails in the calc group. So all of those numbers of successes and fails are at least 10, so that condition is met. And that assumes or shows us that the shape of the sampling distribution is approximately normal. And the last thing we need is independence. So we're assuming here that our two samples are independent from one another. And we're also assuming that there's more than 1,200 stats and 1,000 calc students is assumed, and that is safe to assume. Now that our conditions are met, we're ready to make our calculation. So here's our formula again for the confidence interval. It's p hat 1 minus p hat 2, the estimated difference in the proportions for the two groups. Plus or minus z star, critical value, that'll come from the table, times our standard error. And so altogether, that's going to give us our confidence interval. So what we're going to do is we're going to take that big formula that kind of might look kind of scary and substitute in the parts we know. P hat 1, the proportion of stat students taking the exam, 0.75. Minus p hat 2, proportion of calc students taking the exam, 0.65. Plus or minus z star, we're going to get that from the table. So 90% confidence, z star is 1.645, times that standard error, p hat 1, 0.75, 1 minus p hat 1, 0.25, over n1, 120, plus p hat 2, 0.65, times 1 minus p hat 2, 0.35, over n2, which is 100. What I tend to do is calculate this margin of error part first, do the 1.645 times this whole thing separately, look at the difference separately, and then combine those in the end. So the estimated difference is 0.1, which means that we estimate that 10%, there's going to be a 10% difference in those proportions, or more stat students will take the exam than calc students. Plus or minus, this margin of error is 0.102, and so that's how much we expect our estimates to deviate. If you then add or subtract the differences, you'll get your confidence interval from negative 0.002 to positive 0.202 would be the difference in proportions. Now, what that would mean is that about 0.2% less of stat students to upwards of 20.2% more stat students would plan to take their AP exam. Now let me show you how to find that on the Inspire. So if you do have an Inspire handy, well, you can run this interval in a calculator page. So we'll add calculator and go into our menu for statistics, 6, confidence intervals, 6, and then this is called the TwoProp Z interval. That's in menu 666. So I hope you're not superstitious. I'm not superstitious, but I'm a little stitious. Successes 1, there were 90. And N1, there were 120. Successes 2, there were 65 out of 100 was that sample size. Confidence level, make sure to change that if you have something different than 95%. We have 0.9, 90%. So we're going to hit OK. And here's our confidence interval, negative 0.002 to positive 0.202. Also gives us our estimated difference and our margin of error, and also breaks down our proportions, 0.75, 0.65, and our sample sizes 120 and 100. So you can do that instead of running through that whole big formula and calculating them by hand. Either way that you do it, you should get the same interval. And in step 4, we will interpret what that interval means. So the interpretation will sound the same as the other interpretations for confidence intervals. We are 90% confident that the interval from negative 0.02 to positive 0.202 captures the true difference in proportions of AP stats and AP Calc students who plan to take their exam. And we subtracted stats minus calc. And what that means, in other words, is that it's plausible that 0.2% less to 20.2% more AP Stat students plan to take their AP exam compared to AP Calc students. One last question here about that interval. Is it plausible that a larger proportion of Stat students plan to take their AP exam compared to Calc students? And really what we're looking for is if this interval is entirely positive, that gives us evidence to say that it's plausible that more Stat students plan to take the exam. Whereas if the interval was entirely negative, that would give us reason to believe that less Stat students plan to take their exam compared to Calc students. Now, this interval is mostly positive, but it does include some negative values, and so it's not entirely positive. So we would answer that question, the best way to answer that would be to say something along the lines that since the interval contains 0, or in other words, it contains both positive and negative values, that means that it's plausible that there is no difference in the proportion between those two groups. Or in other words, that it's plausible to expect that Stats and Calc students will take their exam at an equal rate. So it is not reasonable to say that a larger proportion of Stat students plan to take their AP exam. So just to recap here, some of the important things that we've been covering in this video are the new formulas for calculating a standard error for a confidence interval for two proportions. It's all about comparing two separate populations and how different are the proportions for those two populations. So I know that's a lot of stuff all in one video, but go back and watch it again if you need to. I'm going to share out another video with you the next day or two about significance tests and about working with two separate populations.